Hello everyone, welcome back to another video. In this video, we'll go over some basic terms of simple harmonic motion. So here we have a mass spring system, which is a typical example when discussing this topic. Notice its motion. It periodically moves from its mean position to max stretching, and then to maximum compression, and then back to mean. Now this repeated motion is one complete oscillation. Oscillation is just a repetitive motion. It happens at a very predictable rate, and you can find out how long each cycle of the oscillation lasts. Displacement is the distance of the object from its mean position, but the direction of it depends on which side it is. In this example, I'm taking any motion to the right as positive displacement and any motion to the left as negative. So even if the object moves only slightly to the right from the mean position, it is in positive displacement. And even if it moves slightly to the left from its mean position, then it's in negative displacement. And we have the amplitude, which is the maximum distance from the mean position. In this example, I've taken it to be 15 units. Okay, now let's just rotate the spring system a little bit. And this gives us the image that you're seeing right now. And this is what you would see if you took snapshots of this spring mass oscillation at regular intervals. Except that we are doing it vertically right now. Now notice the shape of those snapshots. It kind of looks like a sine graph. In fact, it can be plotted as a cosine graph, which you can see very clearly with this graph. Now, this insight allows us to turn this phenomena into math that we could use to predict the motion of any oscillating object, not just the mass spring system. So if I just take the cosine graph and put it on a coordinate axis, we make it much easier to deal with all of these oscillating problems. Now we have everything that we need to know summarized by a simple graph. The maximum height of the graph from 0 is its amplitude. The time taken for one complete oscillation, which is from 0 to 2 pi, that is the period. And the number of oscillations in 1 second is the frequency. Now this frequency can be denoted differently as well. Now notice that each oscillation covers 2 pi radians. And for our purposes, we are going to take two oscillations in 1 second. Now that means in 1 second, it covers 2 pi radians, angle of 2 pi radians, twice, which is its angular frequency. Now angular frequency is simply the number of times an oscillation covers 2 pi radians. And that is given by the symbol omega, which is usually written as W, but with curves. Now this could be summed up mathematically. Now this entire graph could be summed up by the following equation, where omega is the angular frequency. Now you might wonder, why do we need to know omega? And why did I write frequency as angular frequency? Well, let's just do some math. So let's just write frequency as 1 by time period. And now omega becomes 2 pi by t. Plugging it back into the main equation, this gives you a much clearer picture on what's happening. So what this says is every time the time becomes a multiple of time period, like 0.5 seconds or 1 second, the graph will reset. as in it will have completed one complete oscillation. So right there, every 0.5 seconds, the graph resets. So 1 second passed, the graph resets. 1.5 seconds passed, the graph resets. And this is because this oscillation has a time period of 0.5 seconds. Now this is a very elegant way to visualize simple phenomena, and it's very fun nonetheless. Thanks for watching, and if you enjoyed, like and subscribe.